In the earlier lectures on Hamiltonian mechanics, we have developed the Hamiltonian from Lagrangian using Legendre transformation, and then we have developed the Hamilton's canonical equation, the set of 2n first order differential equation which replaces the n second order differential equation of Lagrangian formalism. We have also studied few properties of Hamiltonian and we have also discussed Roth formalism, which is especially helpful when the system involves few cyclic coordinates, and for cyclic coordinates we go for Hamiltonian mechanics, and for non-cyclic coordinate we solve the problem via Lagrangian mechanics. So Roth formalism is a admixture of Hamiltonian and Lagrangian formalism. Today we shall discuss yet another aspect of Hamiltonian mechanics, that is the Poisson bracket. The Poisson bracket actually allows us to write the equation of motion in a symmetric form, and furthermore it helps us to make a transition from classical to quantum mechanics. Let us introduce the Poisson bracket. We consider two dynamical quantities. U is a function of set of Qi's, Pi's and of T, which we write in short as U, Q, P, T. This means it is a function of n Qi's, n Pi's and of time T. And similarly we have another dynamical variable V is a function of Q, P, T. The Poisson bracket, the definition of Poisson bracket is that UV, the Poisson bracket of UV with base P, Q, P is sum over I is equal to 1 to n del U, del Qi, del V, del Pi minus del U, del Pi, del V, del Qi. So this sum runs from 1 to n, the number of degrees of freedom of the system. This is the fundamental definition of Poisson bracket. Later on we shall see that it enables us to write equations in a very compact form. Few properties that immediately follows from this definition is the, one more thing. Generally these subscripts, subscript Q and P refers to the basis in which the bracket has been evaluated. For the sake of brevity, one generally omits these subscripts and writes just Poisson bracket as UV. One properties of Poisson bracket is this. UV is simply minus VU. You see that if we interchange the dependent variable, there is a change in sign which leads to this. Another thing is that if you consider the Poisson bracket with respect to a constant quantity, if C be a constant, then this term is 0, and in this case this term is 0. So Poisson bracket with a constant is always 0. And another property is that Poisson bracket of a quantity with itself is also 0. These are the very trivial properties of Poisson bracket. These are very trivial properties, and the linearity property, if we call that AU plus BV, and there is another function CW. Where A, B, C are constants, then it is SCUW plus BCVW. This is the linearity property of Poisson bracket. The product rule is like this. UVW is equal to that is this is the product rule. Recall that in the case of commutator bracket of quantum mechanics, we got the similar expression, but in quantum mechanics these quantities were operators corresponding Hermitian operator, and in that case this ordering was a must. But here in classical mechanics, U, V, W are dynamical variables, so we may write U over here as well as over here in case of Poisson bracket. Similarly, V can be written over here or over here, but we do not want to forego or forget our practice that we have learned in quantum mechanics, so we retain the ordering as it is. It is not at all a wrong way of writing this. So this is the few basic properties of the Poisson bracket, and then I am coming to some involved properties. Say R is a quantity on which U, V and these quantities P, Q depend. Say R is time, then it can be shown that del R of UV is equal to commutator bracket of del U del R V plus U del V del R, as if the rule of differentiation in the case of product of two functions, this is a similar property. We shall prove this property. These are the trivial cases and we shall prove this one. And there is another property very important in the case of Poisson bracket, which we shall quote without its proof, because the proof is a bit involved, and the interested person can consult any standard textbook on Hamiltonian mechanics for the proof of this property. This is U VW plus, note the ordering, the cyclic ordering is maintained. This is known as Jacobi identity. Jacobi. These are the basic properties of Poisson bracket. Before going to any further discussion of Poisson bracket, I shall prove this problem and this property and this property, these two, because others are very trivial and need not require any special attention. So let me first to come to the product rule and then the differentiation rule. So UVW, as per this definition, summation over I is equal to 1 to n del Qy operating on UV del W del Pi del Pi operating on UV del W del Qi. This is the basic definition. For U has been replaced by UV and V is by W. Now we will break this into two terms. This is U del V del Qi plus V del U del Qi. This is the first term, del W del Pi. Then coming to this, U del V del Pi plus the second term is V del U del Pi del W del Qi. So there are four terms. We couple these. I is equal to 1 to n. So first we take these two terms. So taking U common, we have del V del Qi del W del Pi, and from this term del V del Pi del W del Qi. Here we have considered these two terms, and from the other two terms we take V out and we have del U del Qi from this term, and this is del W del Pi minus del U del Pi del W del Qi. If we take U out, this thing is a Poisson bracket of V with W. So this is U taken out, Poisson bracket of V with W, and from this if we take U out, this is Poisson bracket of V and W, and if we take V out, this is the Poisson bracket of U and W. So this is the product rule. Now we shall prove the differentiation rule. So we consider the Poisson bracket of two variables U and V, and we differentiate it with respect to R. So our objective is to calculate del R of UV. So this is basically del R summation over I is equal to 1 to n del U del Qi del V del Pi minus del U del Pi del V del Qi. This is the definition of Poisson bracket. Then we operate this del R. So when del R operates on it, it operates twice. Once on this, this is summation over I is equal to 1 to n del R operating on Now you consider this first term. This is del 2U del R del Qi del V del Pi plus del U del Qi del 2V del R del Pi. These are the two terms originate from the first term, and there are two more terms, del 2U del R del Pi del V del Qi minus del U del Pi del 2V del R del Pi. These are the two terms originate from the second term. We consider these two terms, and second, we assume that u is a continuous function so that it possesses continuous second order partial derivative, so the ordering may be interchanged. Ordering of differentiation may be interchanged. So that we write this as summation over I is equal to 1 to n. For this term we write del del qi del u del r del v del pi. Here we have assumed that the order of second order partial ordering of the second order partial derivative may be changed, and from this term on the same basis we can write this, we write del del pi del u del r del v del qi. This is the term originating from this. Plus there are two terms here. This is del u del qi del del pi operating on del v del r, and from this will be minus sign because there is a minus. This is del u del p del u del pi, and this is this was q, so this is q. This was a mistake. Please make the correction. So this is del u del pi del del qy operating on del v del r. If you collect these two terms, this is the Poisson bracket of del u del r with v. So this is del u del r with v, and this is the Poisson bracket of u with del v del r. Which proves the differentiation law of Poisson bracket. Now we shall consider these are the some basic properties of Poisson bracket, which will be used in the course of this lecture. Now we come to what is known as fundamental or elementary Poisson bracket. By fundamental or elementary Poisson bracket we mean when the Poisson bracket for which at least u or v is one of the canonical variables, say q and p. So these are known as the fundamental or elementary Poisson brackets. Fundamental Poisson bracket. We consider this Poisson bracket. This is QKV. So by definition it is del q, this is summation over I is equal to 1 to n del qk del qi del v del pi minus del qk del pi del v del qi. In Hamiltonian mechanics, p and q are treated as the independent variables, so this part is 0. because q does not depend on momentum, and this is del q k del pi, so this is delta of ik, so that this relation becomes summation over I is equal to 1 to n delta of ik del v del pi. When the sum is carried out, this is simply del v del pk. This is one of the relation, and if you reverse the order, a minus sign will come. Similarly, we consider this Poisson bracket pkb. By definition, it is summation over I is equal to 1 to n del pk del qi del v del pi minus del pk del pi del v del qi. Now, with similar logic, P is not a function of Q and Hamiltonian dynamics, so it is 0, and this gives you a delta function delta of ik, so that this becomes minus del v del qk. If we further write in this expression, say in this expression, we consider this with v is equal to ql. If we write v is equal to ql, then we have qk ql is equal to del ql del pk, which is 0 for all k and l. Similarly, if we write v is equal to, if we write v is equal to ql, if we v is equal to ql, or sorry, v is equal to, if we write pl, then we have pk pl is equal to minus pl qk, which is 0 again for all ik. One interesting case arises, however, if we consider this expression, and if we consider this with v is equal to pl, then we have qkpl, then we have del v, that is del pl del pk is equal to delta of lk. Similarly, if we consider this expression with v is equal to ql, v is equal to ql, we have pk ql is equal to minus del ql del qk is equal to minus delta of lk. These are the same relation. So what we see, the formula is that qi qj is equal to 0 is equal to pi Pj for all I and j. And the most important property is that Qi Pj is equal to delta Ij. This relation exactly looks like the commutator bracket involving fundamental quantities. Recall in quantum mechanics we had Qi dot Qj dot commutator bracket is a 0, null operator is equal to Pi Pj, and we have Qi Pj. This is our H cross identity operator, the uncertainty principle. This set of classical relations in terms of Poisson bracket looks very similar to the commutator relation of quantum mechanics. That is what we have said, that the passage from quantum to passage from classical to quantum is best done through Hamiltonian formalism when written in terms of Poisson bracket. Here we have come very close to a nice expression, that is if we consider these two relations. So this relation, we recall that this is del V del Pk, and if we call this relation, this is del V del Qk. So we now write for V, we write H, the Hamiltonian of the system. If we set H, then you see what we get. So we write with QKH this relation. What we get is equal to del H del Pk. Del H del Pk, we know that del H del Pk is the Qk dot, the Hamilton's canonical equation. And this equation with V is equal to H, we get Pkh is equal to minus del H del Qk, which is we know again, that is Pk dot. So we see that this is the symmetric form of Hamilton's canonical equation. Symmetric form of canonical equations. In original form, the when we write Hamilton's canonical equation, then this is plus sign and this was a minus sign. But when we write this equation in terms of Poisson bracket, they are the same sign, so we call it a symmetric form. Now we come to the equation of motion. This is one advantage of writing for the equation of motion in terms of Poisson bracket. And the equation of motion, if we consider a variable, dynamical variable A, which depends on the generalized coordinates, momenta and time, then we get equation of motion. We consider a quantity which is a function of set of q's, set of p's and of t. Then the dA dt, the total time rate of change of A is del A del t plus. Since it depends on all the q's, we write it as I is equal to 1 to n del A del qi del t plus del A del pi del t. So this is del A del t plus this is I is equal to 1 to n del A del qi. This is qi dot plus del A del pi dot. We write Hamilton's canonical equation here. Del A del t plus summation over I is equal to 1 to n del A del qi, which were there in the earlier steps, and we write for this del h del pi to replace qi dot. Then this part is del A del pi, and for this we have del h del qi with a negative sign. So which is the Poisson bracket? So this is del A del t plus Poisson bracket A with h. The Heisenberg equation of motion is very similar to this. The difference between these, that in quantum mechanics the operator A are replaced by the classical mechanics of dynamical variable A is replaced by the Hermitian operator, and this Poisson bracket is replaced by commutator bracket, and there is the quantization through the vector h cross. So there will be a IH cross factor arising over here. So this is the simple difference between the equation of motion in Hamiltonian mechanics using Poisson bracket formalism and that in quantum mechanics. Actually in quantum mechanics the relation is del t is equal to del A prime del t plus 1 over IH cross AH. These are the commutator brackets. Now we come to the equation of motion. If A doesn't have any explicit time dependence, in that case this is 0, and furthermore if the Poisson bracket of A and H is 0, then dAdt is 0 and A is called a constant of motion. If del A del t is equal to 0 and the Poisson bracket of A with the Hamiltonian is 0, then dA dt is 0, A is equal to constant of motion or a conserved quantity. It is very interesting to note that dH dt can be written as this equation. We get dH dt is equal to del h del t plus h Poisson bracket, which is simply del h del t. And if h doesn't have any explicit time dependence, then h, the Hamiltonian, is a constant of motion. In the next class, we shall consider the Poisson bracket involving angular momentum operator to come to an end of the Hamiltonian dynamics.